Hi everyone, welcome back to the channel. Today we are tackling a challenging redox reaction by learning how to balance it using the half reaction method. Grab your writing materials, let's dive in. First, let's quickly review what a redox reaction is. Redox stands for reduction and oxidation. I repeat, redox stands for reduction and oxidation. Therefore, a redox reaction is a reaction in which oxidation and reduction take place simultaneously or at the same time. Now, what is reduction? We're at reduction. What is reduction? Reduction is gain of electrons or decrease in oxidation number. Gain of electrons or decrease in oxidation number. And to make it memorable, reduction equals RIC. RIC. Reduction is gain of electrons. RIC. Reduction is gain of electrons. Let's move to oxidation. If reduction is gain of electrons, therefore oxidation is the loss of electrons. And if reduction is decrease in oxidation number, therefore oxidation should be increase in oxidation number. And equally, to make it memorable, oil. Oil equals oxidation is loss of electrons. Oil, oxidation is the loss of electrons. We are going to learn how to balance redox equation by working with an example. Balancing redox equation is a little different and tricky from balancing a normal chemical equation because we have to balance both atoms and charges, and we are going to see that with the equation on the board. So let's see how we can balance this equation on the board. Let's look at how the oxidation states or number of some species are gotten. Elements in their elemental form always exhibit an oxidation number of 0. For example, sodium, not the sodium ion or the cation, will have an oxidation number of 0. Or for instance, chlorine, not the chloride ion or the anion, will have an oxidation number of 0. All the group 1 elements will have an oxidation number of +1. All the group 2 elements oxidation number of +2. The halogens always exhibit an oxidation number of -1, except when they are bonded with oxygen. Monoatomic ion, for instance, sodium ion, will always take the charge of the ion. Sodium ion is written as Na+. So the oxidation number will be +1. For instance, magnesium ion, it is written as Mg2+. So the oxidation state or the oxidation number of magnesium as the magnesium ion will be +2. The halogens equally exhibit an oxidation number of -1, except when combined with oxygen. And then oxygen always exhibits an oxidation number of -2. You should know the oxidation state of oxygen because most of the compounds in redox reaction always have to deal with oxygen. So we are saying that the oxidation state of oxygen when combined in a compound will always be -2. Next, sum of the oxidation state in a neutral compound is always equal to 0. For example, a neutral compound like carbon dioxide, A neutral compound is a compound with no charge. It is not negative and it is not positive. It is just neutral. For example, carbon dioxide. The sum of their oxidation state will always equal to 0. And that one is sodium chloride, sodium carbonate, and so on and so forth. And for polyatomic ions, what are polyatomic ions? Polyatomic ions are ions that are made up of 2 or more different atoms. Ions meaning they have a charge. They can either be negative or positive, and they will always take the charge of the ion. They will always take the charge of the ion. This is a redox reaction on the board, meaning it is undergoing oxidation and reduction. And our job is to identify which element is undergoing reduction and which is undergoing oxidation. First and foremost, we are going to determine the oxidation number of all the species involved in this reaction except for oxygen and hydrogen. I repeat, we are going to determine the oxidation number of all the species involved in this reaction except for oxygen and hydrogen. From the values we will have, we can then proceed in identifying which species is undergoing oxidation and which is undergoing reduction. So let's identify our atoms other than hydrogen and oxygen. We have carbon here on the oxalate ion. On the permanganate, we have manganese. Carbon dioxide, we have carbon. And manganese too, we have manganese. So we have identified our atoms other than hydrogen and oxygen. These are the atoms we have here. I repeat, on the oxalate ion, we have carbon. Oxygen is not there because we are given an exception to oxygen. Permanganate, the same thing, exception with oxygen. Manganese too, we only have manganese, and then carbon dioxide, we have carbon. Note that we are accepting oxygen and hydrogen. So these are the atoms we'll be working with. We have identified our atoms. Now let's proceed in calculating the oxidation state of all the atoms we have here on the board. So we are beginning with the oxalate ion, the first compound, C2O4 2 minus. So we are going to have our 2C because we have C2. So there are 2 carbon atoms in that compound plus 4 oxygen atoms because we have O4, meaning there are 4 oxygen atoms. And then we are going to equate it to the charge of the polyatomic ion, which is -2. Remember that we are still trying to calculate the oxidation state or the oxidation number of carbon in this compound. Also recall that I had previously stated that the oxidation number of oxygen in all its compound is -2. So we are going to substitute -2 in the place of oxygen and we still equate to our charge. Now it is the mathematical part. If we do our mathematics well, multiplying and collecting like terms and unlike terms the other way, we are going to have our C, the oxidation number of carbon, as +3. The oxidation number of carbon will be +3 plus 3. We have calculated the oxidation number of carbon on the left hand side of the equation as +3. Now let's go to the right hand side of the equation and still calculate the oxidation number of carbon. let's finish with all the carbons before we move to manganese. On the right hand side, we have carbon dioxide. Carbon dioxide is not a polyatomic ion like oxalate. Carbon dioxide, if you remember so well, is a neutral compound. And I said the sum of their oxidation number should be equal to 0. Still, oxygen still have an oxidation number of -2. And when we substitute and do the mathematics, carbon is going to give us an oxidation number of +4. We are done with calculating the oxidation number of all the carbons in the compound. Now we are going to continue with calculating the oxidation numbers of the manganese. And first we are beginning with permanganate ion. We are going to calculate the oxidation state of manganese in permanganate ion. So we are going to write our manganese plus 4 oxygen atoms. There are 4 oxygen atoms in permanganate ion. We are going to equate to -1 because the charge on that polyatomic ion is -1. We remember that oxygen always have an oxidation number of -2 in all its compound. That's why we are substituting -2 in place of oxygen. When you take 4 times -2, it's going to give you -8. And then when you take your -8 the other way, where that 1 is going to be +8. When it crosses the equal to sign, it changes, the sign changes from negative to positive. And 8 minus 1 is going to give you +7. So we are saying that the oxidation state of manganese in permanganate ion is +7. We continue to the last and the least. The last and the least is manganese 2. It's an ion, manganese 2. And if you recall very well, there's nothing we have to calculate here. We said the charge of a monoatomic ion is the oxidation number of that ion. So since the charge of manganese 2 is +2, the oxidation number will equally be +2. Now that we have successfully calculated the oxidation numbers of all the species involved in this reaction other than hydrogen and oxygen, we can then proceed to identify which species is undergoing oxidation and which is undergoing reduction. If we remember very well, our oxidation was defined as loss of electrons or increase in oxidation number. If we looked at carbon very well, the oxidation number has increased from 3 to 4. An increase in oxidation number is oxidation. And if we look at manganese, the oxidation number has reduced from 7 to 2. That's a reduction, and it is a reduction reaction. So let's write our half equation for oxidation. This is our half equation for oxidation because the oxidation number of carbon in oxalate ion was 3 and then 4 in carbon dioxide. That was an increase in oxidation number from 3 to 4. In oxalate 3 and in carbon dioxide 4. So this is our oxidation half equation. Now we have to balance this oxidation half equation balancing the number of atoms and the number of charges. Let's look at the equation again. On the left hand side of the equation, we have 2 carbons, but on the right hand side, we have just 1 carbon. On the left hand side again, we have 4 oxygen atoms, and on the right hand side, we have just 2 oxygen atoms. So we are going to write a 2 in front of carbon dioxide, and that will be balanced. Let's double check to make sure that the number of atoms are balanced. On the left hand side of the equation, we have 2 carbon atoms. On the right hand side, we have 2 carbon atoms. On the left hand side, we have 4 oxygen atoms. And on the right hand side, we have 2 times 4. The 2 in front works for carbon and for oxygen. So it is 2 times 4, which gives us equally 4 oxygen atoms. So our number of atoms are balanced. Now, let's move to calculate or to balance the number of charges, because on the left hand side, we have an overall charge of -2, and on the right hand side, we have an overall charge of 0. I would like us to calculate or balance the charges by using the oxidation numbers of carbon in oxalate and in carbon dioxide. Remember that the oxidation number of carbon in oxalate was 3, and now we have 2 carbon atoms. So we are going to multiply the oxidation number by 2, and that will give us +6. Also remember the oxidation number of carbon in carbon dioxide was equally 4. And now we have how many carbon atoms? We have 2 carbon atoms, and that gives us 4 times 2, which is 8. Since our number of atoms have increased, our oxidation numbers too have increased, from +3 in oxalate to +6, and from +4 in carbon dioxide to +8. But in balancing redox, we said we must also balance for charges. How do we balance for charges? We balance for charges by adding electrons. I repeat, we balance for charges by adding electrons. Let's look at the equation we have on the board. On the side of oxalate ion, on the left hand side, the oxidation number is +6, and on the right hand side, that the side for carbon dioxide, the oxidation number is +8. How do we do to make sure that they are equal? We either have +6 on both sides or +8 on both sides. Now, let's start adding our electrons. We know that the difference is 2. If we have to add 2 electrons on the side of +6, we know that electrons are negatively charged, meaning we are adding -2. The charge on the side of the oxalate is going to go down to +4, because +6 minus 2 is equals to +4. Let's come down to the side of the carbon dioxide. We have +8. Let's add 2 electrons to see what we will have. If we have +8 minus 2, electrons are negatively charged, is going to give us +6, and that is what we wanted. So we are going to add 2 electrons on the side of the carbon dioxide, because adding it there gives us the charge of +6, which is equal to the charge on the left hand side. So we have +2, meaning we are adding 2 electrons. +8 minus 2 gives us +6, and our equation is balanced both in atoms and in charges. We have balanced our half equation for oxidation. Now, let's move to the half equation for reduction. We still remember that the species that was undergoing reduction was manganese. The half equation for reduction: manganese being reduced from 7 in permanganate to +2 in manganese 2 ion. That's the equation we have on the board. Now we start balancing our number of atoms. If we look at the left hand side of the equation where we have permanganate, we discover that we have 1 manganese there. And when we look at the right hand side of the equation, we equally have 1 manganese. So manganese is balanced. But let's look at the left hand side again. We have an oxygen atom which is not found on the right hand side. How do we then balance for oxygen atoms? Are we supposed to add oxygen atoms to the right hand side? Of course not. How do we balance for oxygen atoms? We balance for oxygen atoms by adding water. I repeat again. We balance for oxygen atoms in acidic medium by adding water. So we are going to add water to the right hand side of the equation to balance for oxygen. Since we have 4 atoms of oxygen on the left hand side, we are going to add 4 molecules of water on the right hand side, and that is going to balance our oxygen. We know that water is oxygen and hydrogen. We are indirectly equally introducing hydrogens on the right hand side. So we have to balance again for the hydrogens we have introduced, and we balance for hydrogen by adding hydrogen ions. We balance for hydrogen by adding hydrogen ions. We balance for oxygen by adding water, and we balance for hydrogens by adding hydrogen ions. So we are going to write our 4 molecules of water because we have 4 oxygen atoms, and in adding the 4 molecules of water, we have indirectly introduced 8 hydrogen atoms. And I said we balance for hydrogen atoms by adding hydrogen ions. So we are equally 4 times 2 will give us 8. So we are equally going to add 8 hydrogen ions on the left hand side, and everything is balanced. Let's cross check. We have 8 hydrogen ions on the left hand side, and we equally have 8 hydrogens on the right hand side. We have 1 manganese and we have 1 manganese. We have 4 oxygen atoms and we equally have 4 oxygen atoms. So our atoms are balanced. We are going to proceed in balancing our charges. After balancing our charges, our equation will be balanced. Actually, there are so many ways of balancing for the number of ions or charges in a redox reaction, but I want us to stick to the first one we have been using, or the first one we used when we are balancing for oxidation half reaction. And remember that we use the oxidation numbers that we calculated. Now, the oxidation number of manganese in permanganate ion was +7. Remember that was +7. And the oxidation number of manganese in the manganese 2 ion was 2. Equally remember that we balance for charges or ions by adding electrons. When you look at +7 and -2, the difference between them is -5. So we are going to add 5 electrons to the +7 to make sure that the charge should be 2. Look, we cannot add 5 electrons to the side of the 2. If we add 5 electrons, it's going to take us to -3. It's going to give us a charge of -3, which is not equal to +7. But if we add -5 this way, it's going to give us a charge of +2, making the charges to be equal. I take it over again. We balance for charges by adding electrons. On the left-hand side of the equation, where we have permanganate ion, the charge was +7. And on the right-hand side of the equation, where we have manganese 2 ion, the charge was +2. Since we say we balance for charges by adding electrons, so we are going to add electrons. Electrons are negatively charged to the side of the +7. When you add 5 electrons to the side of the +7, you are going to have 7 minus 5, which will give you +2. And on the right hand side, our charge is +2, and of course our charges are balanced. These are our half equations for oxidation and reduction. But we are not done yet. No. Look at the equations. We said oxidation was loss of electrons and reduction was gain of electrons, meaning the number of electrons lost during oxidation must be equal to the number of electrons gained in the reduction reaction. When we look at the oxidation reaction, we are seeing just 2 electrons that we are given off, that we are lost during oxidation. Now let's come back to the reduction. We are seeing 5 electrons gain. So we need to make sure that the number of electrons given off during oxidation should exactly be equal to the number of electrons gained in reduction. How do we do that? We are going to multiply all the species in the oxidation reaction by 5 because of the 5 electrons, and all the species in the reduction reaction by 2 because of the 2 electrons, meaning we are just swapping the value of the number of electrons. 2 is going to multiply the reduction equation, and 5 is going to multiply the oxidation equation. Let's start with the oxidation reaction. When we multiply the oxidation reaction by 5, we are going to have 5 oxalate ions, and we are going to have 10 carbon dioxide. 2 times 5 is 10, and we are equally going to have 10 electrons. Let's go to the reduction half equation. When we multiply all the species by 2, we are going to have 2 times permanganate ion plus 2 times 8 is 16. We are going to have 16 hydrogen ions, and we are equally going to have 2 times 5, 10 electrons. You see now that the number of electrons are balanced. We continue. 2 times manganese 2 ions, and then we have 2 times what? 4 water. 2 times 4 is 8. We are going to have 8 molecules of water. And then we are going to rewrite our equation using the one below our topic, balancing redox reaction in acidic medium. So we are going to write our equation in that format. So we are going to have 5 oxalate ions. We are multiplying the permanganate by 2. 2 permanganate ion, and then we move to the hydrogen ions. We are multiplying the hydrogen ions equally by 2, which will give us 16. We are just going to follow that format and write out our equation. To save time, let me just write it. At least I've explained. And then next, we are going to cancel the number of electrons. We are going to see that we have 10 electrons on the right hand side and 10 electrons on the left hand side, and they are going to cancel out. I hope this video was helpful. Thanks for watching and see you in our next video. Don't forget to like and subscribe to my channel for more chemistry tutorials.